Algebra 2 students, Mrs. Myers here. We are working today on lesson 16, which is the last lesson we need to go through for mod 2. So what I've taken the liberty of doing for verifying trig identities is reminding you of the different identities that we have worked on so far that we're going to be needing to make substitutions here. So they are your Pythagorean identities, the reciprocal identities, and the quotient identities. Feel free to pause the video and copy them down right now if you need to, or if not, that's fine if you don't copy them down, because really you already copied them down with previous lessons. All right, so let me show you what our first example is so that you have an idea of what an identity looks like, and then I'll explain to you what the process looks like. So we've got tan theta is equal to secant theta over cosecant theta. Okay, so that is our first identity. So this looks like an equation, okay, but we're not going to treat it like an equation, meaning that what we typically do with equations is we solve them, but notice that's not the directions. It doesn't say solve the equation. There is such a thing as solving trig equations, but right now we're not doing it. It's verify the identity. So when it says to verify the identity, what you're basically thinking about is really how an equation is just two expressions that are set equal to each other, and you are trying to verify that the expressions are mathematically equivalent to each other. So how you do that is you work on one side of the equal sign or the other. Okay, you pick one of the expressions to algebraically manipulate and match the other one. Now, I always suggest you pick the side that's more challenging to work on, one's a little more complicated. Okay, that's the side that typically is something that you can do with it. So in this case, I would say it's the right-hand side. And the first thing that I'm hoping that you see when looking at the expression here on the right-hand side is that the numerator and denominator are each reciprocal functions. So let's make those substitutions, okay? Secant theta is 1 over cosine theta, and cosecant theta is 1 over sine theta. Now, by doing that, yes, we've created a complex fraction. It's a fairly easy complex fraction. That is just one fraction being divided by another fraction. So what you want to do is you want to take this and write it as 1 over cosine theta times sine theta over 1, because hopefully we all remember that division by a fraction is the same as multiplication by the reciprocal. Now, there are no factors to cross reduce out, so we're just going to multiply straight across the numerator, straight across the denominator, and we get sine theta over cosine theta. And what we hopefully know about sine theta over cosine theta is that it is tangent theta. And if we take a look at the other side, that is exactly what it says. So now we are able to finish off with the last line of our identity being tan theta equals tan theta. And we're all set. All right, so that was a little on the easier side. So let's get to some that are a little more challenging. We got some few more examples to go through. All right, so we got sine squared theta over 1 minus cosine theta. And that's equal to 1 plus cosine theta. Okay, so again, we're going to verify this identity. So just start by drawing that line right down where the equal sign is. So you just remind yourself that, you're not solving an equation here. You're just showing that one of these mathematical expressions is equivalent to the other mathematical expression. So again, I suggest you pick the side that's more challenging to work on. Okay, the side that has more going on, and that would be the left-hand side here. And we got to be careful not to make any errors. So one of the first things that I want to point out, a mistake that I've seen students make before, is to try to split this up into separate fractions, and that is not okay. If it was reciprocated from what it is, meaning if the binomial was in the numerator and the monomial was in the denominator, then we can split it up, but we can't split it up like this, okay? So what we're going to do, it's all about making substitutions and performing algebraic maneuvers, is this numerator, sine squared theta, okay? As soon as you have a trig function that is squared, you can go to your Pythagorean identities, and typically this is going to be helpful. So let's see how we can make substitution for sine squared theta, and that is if we write, think about minus and cosine squared theta each side. Okay, we can get sine squared theta equal 1 minus cosine squared theta from that identity. So that's what we're going to do. We're going to make that substitution. Now, from there, be careful not to make another mistake that I've seen students make before, which is to divide out terms. Okay, no such thing as ever dividing out terms. You only divide out factors. So with that being said, the numerator is now an expression that can be factored. It is a difference of perfect squares. Okay, always want to think of these. Okay, the substitution that you get very often from these Pythagorean identities are difference of perfect squares, and difference of perfect squares always factors into conjugates, right? So we got 1 minus cosine theta and 1 plus cosine theta as the conjugate factors of 1 minus cosine squared theta, right? Because 1 times 1 would be the 1. The negative cosine theta times the positive cosine theta would be negative cosine squared theta. And the other products, okay? Positive cosine theta and negative cosine theta, those would just zero out, right? So we would just be left with, again, 1 minus cosine squared theta if we multiplied these two factors together. So indeed, these are the conjugate factors of 1 minus cosine squared theta. Now, let's take a look at that denominator. So I'm going to put it in parentheses. I don't really need to do that. But by doing that, see how it says identical, right, to 1 minus cosine theta? So we are able to just divide those right out. And we are left with 1 plus cosine theta, which is identical to the expression that we want to get from the other side of the equal sign. So we're all good with that one. All right, so let's try a couple more. All right, so the next one that we're going to take a look at is tan theta sine theta plus cosine theta is equal to secant theta. Okay, so in this case, I think the left-hand side is a bit more complicated. Okay, not credit, but just a bit more going on. So anyway, we've got a multiplication of tan theta sine theta going on here. So let's work with that. So tan theta is sine theta over cosine theta. And when you multiply that by sine theta, and we don't get any cross-reducing going out, but we're going to multiply straight across the numerators and get sine squared theta. Straight across the denominator, get cosine theta. And if we take a look at the other term over 1, we hopefully are reminded that fractions need to have a common denominator to be added together. So we would want this denominator to read cosine theta, right? So that means we're going to come back up here. We're going to multiply by cosine theta over cosine theta, right? That's a form of the number 1, so it doesn't change what this fraction is equivalent to. Okay, it's multiplying by the number 1, but it does allow us to write this as now cosine squared theta over cosine theta, which has a common denominator with the other fraction. So we are going to join those together as one single fraction, and it would be sine squared theta plus cosine squared theta all over cosine theta. And hopefully when we look at this numerator, right, that would look familiar to us over here, right, from our Pythagorean identity. Okay, that is equivalent to the number 1. And what about 1 over cosine theta? Hopefully we recognize that as secant theta. And now we are good to go. All right, so one last example. Okay, let's just get a little bit more practice here. All right, so we are taking a look at 1 plus sine theta quantity squared plus cosine squared theta all over 1 plus sine theta, and that's equal to 2. All right, so I imagine you can guess here that we should work on the left-hand side. Definitely a lot more going on there. So careful of those errors, all right? As soon as you make an error, there's no way you can verify your identity. So, okay, again, just careful of the algebraic maneuvers that you can and can't make. Here, we have a binomial squared. We do not want to just square each term to clear the parentheses. That is not okay, all right? We are going to write this quantity twice, and I do suggest that this is what we want to do here is clear the parentheses, because obviously this is just plain old number 2 over here. So multiplying 1 plus sine theta times another 1 plus sine theta, okay, remember the distributive property, is going to get you 1 plus sine theta plus another sine theta plus sine squared theta, right? So see all that distribution there, and then don't forget that plus cosine squared theta term. That's all over 1 plus sine theta. Now, again, careful of those errors, okay? Don't try to cancel out or divide out common terms. That's never okay, all right? Can't do that if you just look, oh, there's 1 plus sine theta there, there's 1 plus sine theta there, and just cancel right out. You're done for. There's no way you're going to get this to work, okay? So don't divide out common terms. Remember, all you ever get to divide out are common factors. So with that being said, let's simplify the numerator and see what happens. So sine theta plus sine theta is 2 sine thetas, right? And when you look at sine squared theta plus cosine squared theta, we just did that just moments ago, that's the value of 1. So now I'm going to combine like terms in the numerator. 1 plus 1 makes 2. So I have 2 plus 2 sine theta over 1 plus 1 sine theta in the denominator. So it's very, very close here. We're getting really close to what we want to get to. So notice the numerator, both these terms have a 2. So I'm going to factor that out. And when I do that, notice what I have left inside parentheses here when I factor the 2 is exactly the factor that's in the denominator, so we can divide out common factors, and all good. 2 equals 2. All right, so that is the idea of verifying identities. Again, super, super important to keep all this in mind, okay? Making appropriate substitutions is really, really good, and then just careful of your algebraic maneuvers. All right, so I hope the problem set goes well with this, and I hope that you have enjoyed our trig module. Be well.